Good morning. Welcome to this open session of the PAC. We start with a presentation of the proposal on studying lambda interactions in matter by Franco Garibaldi. Please, Franco, go ahead.
Okay, so I start describe the physics motivation, then the theory framework, then I will pass the experiments, and at the end, summary conclusion. Slide 2, please. So our main goal of our experiment is to study the Hadron dynamics in a particular environment. So we have hypernuclei and neutron stars. They are very different objects for dimension, but the same physics. Neutron stars are remnants of the gravitational collapse of massive stars having mass about 2 solar masses. The neutron stars are excellent observations to test fundamental properties of nuclear matter under extreme conditions and offer interesting interplay between nuclear processes and astrophysical observables. Hyperons have to be there. We know that they should appear at certain density when the chemical potential is large enough to make conversion of nucleon to hyperons energetically possible. But we know that the relief of the Fermi pressure due to its appearance makes equation of state stiffer with the reduction of the mass to values that are incompatible with the recent observation. So we need a stiffer equation of states. The next slide, please. So the present understanding of nuclear interaction that involves hyperons is not complete. The reason comes from a combination of incomplete knowledge of the forces, especially the three-body forces, and in the needed use of approximated theoretical many-body techniques. The use of lead target will allow us to investigate hypernuclear dynamics in a new environment in which three-body forces are expected to play an important role. This will allow us, in the framework of a more general approach as quoted previously, to study the hyperon puzzle in a complementary way with respect to the approved proposal on calcium 40, calcium 48. That based in isospin dependence of lambda and m. This scales with the length into something different. In fact, it has been suggested that the three-body forces would provide the additional repulses that you saw that is needed to make the equation of state stiffer enough to help solving the hyperon puzzle, or at least to make a big step towards its solution. Next slide, please. So there is here some calculation by different theorists about the three-body forces. All the calculation by Skirma model that includes three-body force by Milner, and you see here, for example, API dependence and the spacing of single particle energy as function A is needed, and you see how big contribution would be having the data on LED so precise to make this fit at the best. The calculation of Electron show the importance of three-body interaction with respect, and especially if you choose the right one. It is important to choose the right one. This is also what happens with the calculation by Vidania, where you can see that both that there are different, that there is an A dependence of the difference between two-body and three-body forces, and also that you can notice that you can single out also easily which of the three-body forces is the right one, because our resolution we will see is exceptional, so much better than needed for this. But this is also for other calculation by Yamamoto. Next slide, please. So the calculations for astrophysics, you need these three-body forces, and you with the first calculation you go closer to the mass, solar mass needed. Even better is done by calculation by Ronaldoni, AFM DMC calculation, and by Yamamoto with Kinematics calculation. Next slide, please. So what is the panorama of the techniques possible for hypernuclear spectroscopy? You have pion and kaon beams that go on neutron and electron beams that go on protons. This makes one of the difference because you go on mirror hypernuclei. They excite different states. They are fully complementary. What I'd like to underline is here the main characteristics of electron scattering with respect to hadron scattering, that is the missing mass resolution that allowed us, for example, to detect the core-excited states of carbon-12 that is not possible with limited energy resolution. But I'd like to underline once more that the two approaches are fully complementary. We need both of them to study hypernuclei, to study this problem also astrophysics, with astrophysical impact. The next slide, please. So, hypernuclei, this was underlined yesterday also by Gogami, that hypernuclear spectroscopy is the only method that can measure the absolute binding energy for grounded and excited states with a high accuracy that is about 70 keV. And underlining also that energy calibration is important. It's very important, not only energy resolution, but energy calibration. So we are proposing in this proposal to extend the experimental study of kernel production that we have done the last 15 years at the JLab in both OLE and LC to this extreme. That means the LED. This is in a complementary way, as we said, with respect to calcium-40, calcium-48. We want to address the same problem, the hadron puzzle. And okay, this is the dependence is the technique used for the calcium-40, calcium-48. We know that the three body forces are strongly independent. This makes the LED unique suited to study the Lamb interaction in a uniform nuclear medium with the large neutron excess. It's important also to underline that contribution of three-body nuclear forces, which is known to be large and repulsive as needed in nuclear method at equilibrium density, is believed to be much smaller and attractive in calcium-40. This is important to see the complementarity of these two nuclei. Of course, the same might be true for in the strange sector, of course, not only nuclear matter. Okay, so next slide, please. Theoretical framework. Theoretical framework of this experiment has been, interpretation of the experiment has been developed by Omar Benhar in collaboration with Petr Bidzowski and Isaac Vidania, and consists in carry out calculation of the E'-K reactions within the formalism of nuclear main body theory, extensively successfully employed to study proton knockout, that means E'-P reaction. And there is a clear connection between E'-P and E'-K that will allow us to extract information on mixing energy spectra by truly model independent way. Of course, there are other elements of the theory that elementary calculation have been performed by Bidzowski. Microscopic calculation of the lambda spectral function is available for nuclei from helium-5 to lead-208. And of course, cross-section for kinematics, for the new kinematics have been calculated by Motopa and Milner, and these are very reliable because it's the kind of calculation used that they used to give us the cross-section for the other nuclei we have used. We have both done in OLE and in LOC, so they are reliable. So it's important for the counting rate we have quoted and we are putting here. Other calculations have been done by Yamamoto as quoted and others. Okay, next slide, please. So back to the data of end of 80s in Saclay. You can note that the measured charge density distribution of lead clearly shows that the region of a nearly constant density accounts for a very large fraction of nuclear proton. This suggests that we are close to uniform nuclear matter in the nuclear star. Okay? It's very different density, etc. But this you see the difference, and this from lead with zirconium, nickel, calcium, etc. And this validity of this conjecture it's based on the comparison between theory and experiments for the experiments we did at NICEF in the mid-90s. Next slide, please. So what is are these results? These are summarized here, and you see that short-range correlation appear to be the most important mechanism leading to the observed quenching of spectroscopy factor, while surface effect and shell effect play a role only in the vicinity of Fermi surface. But more important is that you can see that the deeply bound protons in the lead ground state are unaffected by finite size and shell effect. So they behave as if they were in nuclear matter. Okay. Now I underline also that what is said before that the relationship between E K and P and the importance of the exact information in the modern independent way. So the use of lead target appears to be uniquely suited to study the lambda interaction in uniform nuclear medium with large neuron excess. And JLab, to our best knowledge, is the only lab where to make these experiments. Next slide, please. So, hydrogen in heavy nuclei, what data we have? We see that this is exceptional good data that I took from a review paper by Hashimoto and Tamura, it's impressive data, for example, up to 89. But as soon as you increase A, especially for lead, you see that the levels are barely visible. So you can do better. You can do better with the prime K reaction because you have better energy resolution and better calibration. Not forget about this important characteristic to measure more precisely the lambda single particle energy towards the goal of our experiment. This was the conclusion by Hashimoto and Tamura in their famous papers. We know from our colleague Nakamura that there are plans at the PAC to produce a high resolution pion beam. This is very good. We would be ready to go there because this is very good because the complementary approach is very important. I don't know if what are the plans there, if are realistic to have in reasonable times this by at underline these complementary approaches is very important. Next slide, please. So here you have the comparison between what you got with pion beams, with the existing pion beam at the time, and you get you would get with E'K on lead for resolution that is around 800 keV, but the same would be with different resolution, as I will show in a moment. So you see how good is the identification of the different levels. And this calculation, this plot were produced by Miller Motova. Each peak, of course, corresponds to several levels based on closely spaced proton states. But you are not interested in this final details. It's important that you can get this S lambda, P lambda, D lambda, F lambda, G lambda, H lambda well determined. This you can. You can separate even the series as two peaks. In any case, you centroid we determined with high precision 70 kV, as you notice. You can see below that this happens, of course, also if you as needed, you draw the quasi-free continuum, so you see that the precision determination stays the same. Next slide, please. So about the apparatus is been described yesterday, so I'm not entering detail by Kogami, but anyway, you see the energy angles of the different apparatus, the progress made with respect to HRS, to OLE, and also because we coupled the best of the two apparatuses, because the HKS is much higher acceptance. This is important for counter-X with respect to HRS. Something I will say about this momentum that is very different from what we got in OLE, 1.2 GV/C, we had 1.9. Anyway, this is resolution calculated by Guido Urcioli, evaluated by Monte Carlo with Urcioli at about 850 kV. And you see here what we are asking for as beam time. We are asking for 20 days to have an exceptional signal-to-noise ratio, that means peak significance, somebody says, the 21. This for the smallest peak, the essential peak. You can imagine what you have with the rest. Of course, this included, because, okay, you need calibration, both what is needed here from calcium and what's described yesterday by Kogami, but these are included in the so what is needed for LED is this 20 days. Next slide, please.
You have 4 minutes left.
Yes, I'm almost finished. So about the target comes from the expertise gained with T-Rex by Silvio Kovrig, and that showed that we can have essentially our 25 microamperes on the target on 100 milligram centimeter square target by cryocooling with no rotation at all. You need at least 25 microamperes. About the particle identification, you have is excellent the system by HKS. You see how many detectors there are. Still the 1.2 GV/C, and you see how good is the PAC rejection ratio. But anyway, we have a much heavier target. So we have a very nice detector that used in OLE very successfully. Which detector is very effective in this case because it's a long way, but I can explain if people is interested in this. Because instead of 1.9 GV/C that we had in OLE, now we have 1.2. This is very effective. That gives us 10 to the 6 PAC rejection ratio only with reach. And let me say also that, just for curiosity, that Chiba University produced an aerogel that gives more double number of photons with respect to Matsushita. We used in Hermes rich aerogel and in HRS and in HKS. Next slide, please. Okay, summary. So, okay, generally saying the nuclear collaboration proposed to PAC 43 some years ago a series of experiments that using the target in a wide range of mass. The purpose was, and still is, the investigation of lambda n and lambda n interaction in variety nuclear media for the impact on astrophysics. This was the goal. The PAC identified first the spin dependence as high priority and said to come back with the dedicated proposal that we in part have done yesterday, in part we are doing now. So we propose to extend the study to the LED to the maximum, and this will allow us to investigate hypernuclear dynamics in a new environment. Three-body interaction are expected to play an important role. This will allow us to study the complementary way the hyperon puzzle with respect to calcium-40. This is very important that we can have accurate theory about this measure retrosection on the well-established, based on established formalism of nuclear memory theory. The lambda and n could provide the additional repulsion making to make equation of state stiffer enough to help solving, or at least making a big progress to understand the hyperon puzzle. This increases, this lambda n increases rapidly with the A. So the LED target is uniquely suited to study the lambda interaction in uniform nuclear medium and show that uniform exists and how close to neutral studies this. And the contribution of gas force, we show that it's repulsive nuclear matter that should be and not so and attractive in calcium. So even if the typical baryon density inside the neutron star is much higher than in the nucleus, a precise knowledge of LED level structure can, by constraining hypernuclear potential, contribute to more reliable prediction regarding the internal structure of neutron star, and in particular their maximum mass. Next slide, please. So, concluding, the proposed measurements, along with the ozone layer hypernuclei, will provide valuable information on YN and YNN interaction. This is the main goal. The proposal, let me note, the proposal is well positioned theoretically and experimentally in the framework of the nuclear collaboration proposal. That means calcium already approved and hopefully approved the few body and the lambda NN presented yesterday. This for the contribution of all of them can give on the best knowledge of lambda N and lambda N interaction and their impact on astrophysics. Finally, let me say, because it is the collaboration is just what is needed for this experiments, let's say, because we know everything about the tools needed to do the experiment, both the hardware and software. Everything has been used as needed, but some target is new, but this is something that has been already discussed there is no problems with all the target we need. Thank you.
Thank you very much. I call on the first reader of this proposal to ask questions. Please, Shinya.
Yes. Well, in the previous slide, you showed the background suppression. So your calculation of the signals to noise ratio 21 is based on the setup without reach. Is it right?
Excuse me. Can you repeat, please? I am in the PID slides. This you are.
Yes.
Okay.
Yes.
So I mean,
in your calculation or simulation of the signals to noise ratios.
Yes.
I understand. My understanding is that you didn't add the reach detector. Is it right?
Yes, this is another value, yes.
So your calculation is based on without reach?
Yes.
Right, okay, thank you very much. So the next is, okay, so your lead target is capable to be installed simultaneously with other targets?
Of course, there is a lot. This has been discussed also yesterday. We discussed this with Dave Makins. I don't know if he's in the audience, but anyway, this is largely discussed. The lead target for this is just the Pyrex-1 that is cryo-cooled, and yes, as a ladder, of course. In the ladder, you can put as many targets as you want. Now we need several of them. You have to discuss details with the target group to see our range, all the targets we want. We need calcium 40, calcium 48, lead. We need all the calibration targets. So this is some discussion has to be done how to arrange and to optimize these layouts. But there are no issues about that. We discussed.
Right, thank you. Yeah.
Further questions?
Yeah, that means
Okay,
I just wanted to kind of drill back a little bit. I mean, I know you have started assembling a collaboration of theorists, right?
Yes.
Is that kind of solidly in place? I mean, I know it's a difficult thing. I even know that Ulf Meissner initiated some collaboration to calculate this, at least in Bruckner-Goldstone in nuclear matter, because it is important. So you are fully, and you had the workshop. I know that. I didn't see that quoted in the proposal, but you have now a collaboration of theorists who follow that and really are working on it.
Yes.
Because that was one of my major criticism 2 years ago, that there was, I mean, nothing, but that is in place. Could you actually kind of, maybe, could you send to an email or to Shinichi just, I don't know if you started a website or something, or actually put together the collaboration or the theory interest group? working
Yes.
now on the problems. That would be nice if you just send this to us.
Yes. We will build a website when we put everything. Okay. All this you at the end. Okay. Just I quoted the year with starts, and in backups, backup you have details of this. You have also in the proposal, but also here you have the details of the all the papers that stay behind this. So we have quite this. I mean, this data are respected by these theories. So there are a lot of people interested on this, and okay, yeah. I think it's interesting.
Okay. Thank you.
Is there any other question from a member of the PAC? That does not seem to be the case. Then I thank Franco very much again. And we turn to the next proposal. Axel Schmidt will present the proposal on precision measurements of A equal 3 nuclei in Hall B.
One moment, I'm trying to get my screen share
Yes.
working. Is that visible?
It's visible. You might even switch off your video transmission because that's just a gray. Now it's not gray anymore. We can see you.
Is it better to see it or better to turn it off?
Up to you. If the bandwidth gets bad, we will let you know.
Okay, sounds good. Let me try to go to full screen. Coming through?
Yes, you're all set. Please go ahead.
Okay, thank you very much for giving me the opportunity to talk about our proposal, precision measurements of A equals 3 nuclei in Hall B. My name's Axel Schmidt. I'm from George Washington University, and I'm joined by other co-spokespeople from MIT, Old Dominion University, Tel Aviv University, and Jefferson Lab. This image I'm showing on this title slide for me really evokes what's really exciting about the A equals 3 system, is that if you study tritium and helium-3, you're looking through the isospin mirror. These two nuclei are an isospin mirror system of each other. If you imagine the proton wave function in helium-3, it's identical to the neutron wave function in tritium, up to charge symmetry breaking, etc. This is really fascinating if you want to understand a few-body system, because by looking at both members of the system, you get information about the complete wave function without having to detect neutrons, which are it's a bit larger hassle. That's not the only reason the system is extremely interesting. If you could imagine studying any isospin mirror system, this one in particular is light, which means it's in range of very, very heavy calculation machinery for calculating the full system. So this is a way to benchmark really serious heavy-duty nuclear calculations. It's also the most asymmetric system you can build a target out of. If you want to study the extremes of proton-neutron asymmetry, what better system to look at than one in which there's twice as many protons and neutrons, and vice versa. Now, this image accompanied a recent PRL that our collaboration put out from a previous iteration of the tritium experiment in which we studied and just scratched the surface of what there is to know. For this reason, I'm going to present our executive summary. What we're proposing to do in this experiment is to do a 60-day experiment with both tritium, helium-3, and a few other targets in class 12. And class 12 will be in the standard configuration with the single electron trigger. We're going to measure quasi-elastic cross-sections over a wide phase space. And this is going to allow us to benchmark few-body nuclear structure calculations. It's going to let us probe short distance and an interaction. It's going to allow us to study reaction mechanisms and quasi-elastic scattering. And we can even measure the neutron magnetic form factor as a bonus. So I mentioned this is a second-generation experiment. There was already the program in 2018 in Hall A. This proposal is going to dramatically extend the scope of that measurement, and it's going to be able to surpass in large margins what we were able to learn. So in this talk, what I'm going to do today is I'm going to show how the impact of the A equals 3 system and show how the Hall A program just showed us a tiny glimpse of what we can learn and how much more there is and why we want to pursue this. Two, it's definitely not straightforward to add a tritium target as the Hall A program put forward, but I'm going to argue that we have a very safe and feasible plan for how we could accomplish this in Hall B, and we've done our homework. Last, I'll talk about the proposed measurements and what we can tackle in 60 days and show that we have a bunch of high-impact observables that will be really fascinating to learn more about. All right, so starting with the A equals 3 system. So studying an isospin mirror system is really interesting for any physics you want to do and where you want to look at isospin structure. Now, we're all familiar with the idea that the strong force is isospin symmetric, but it's not isospin independent. And the classic example of this is the deuteron, where we have a bound system that's spin 1 isospin 0, whereas the dineutron isospin 1 spin 0 is not. So anytime we want to look at the isospin structure of something, an isospin mirror system is great. And one of the things we can look at is the isospin structure of the nucleon-nucleon interaction itself. And specifically, a tool for this are short-range correlations between nucleons. This seems to be a phenomenon that's universally observed in nuclei, all nuclei studied, and about somewhere in 10 to 20% in medium and heavy nuclei of all nucleons are in one of these short-range correlated pairs at any given time. These pairs have high relative momentum. They've got very, very close proximity. And we've learned a lot about them by probing them here in this cartoon with an electron probe by knocking one nucleon out, in which sometimes we can also observe a correlated partner nucleon. Now, the interesting thing about these short-range correlations is they've got a strong preference for being neutron-proton pairs relative to neutron-neutron or proton-proton. And this neutron-proton dominance, or NP dominance, even holds in asymmetric nuclei. I'm showing a figure on the left from a paper that our collaboration put out in Nature 2 years ago, in which we looked in asymmetric nuclei with neutron excesses, aluminum, iron, lead. As you add neutrons, the number of high momentum, short-range correlated nucleons, the neutrons saturate, but the protons are pulled into high momentum states. So even in very, very neutron-rich nuclei, there's this symmetry in this between high momentum protons and neutrons that's maintained. We can see that in looking directly in triple coincidence reactions, that the number of proton-proton pairs is minuscule, the number of neutron-proton pairs is strongly dominant. Now, this is in the momentum range of about 300 to 600 MeV over C. So this is larger than the Fermi momentum, and it indicates that the pair is a short-range pair. And how we understand this is we think about the central part of the nucleon-nucleon potential. At some point, there's going to be a potential minimum between the familiar, attractive meson exchange regime and then what we believe is a repulsive core, which we don't know all that much about. At that minimum, the central force is small, the potential is flat, and here the tensor force dominates. And the tensor force has a predominantly is stronger interaction between spin 1 pairs, and hence this NP preference for which an spin 1 pair is possible without Pauli exclusion. Now, if you ask what happens at even higher momentum corresponding to shorter distances, we now see evidence, and this is a paper our collaboration put out analyzing class data, that the proton-proton pair fraction increases as you go to higher momentum, approaching the scalar limit, indicating that the repulsive core of this force looks scalar. And so what we've done by looking at missing momenta that are much, much higher than the Fermi momentum is we're actually mapping out the isospin structure of the effective NN interaction, which is really exciting. We've even looked in neutrons. So we did the work to do direct detection of neutrons in class, which was not what it was designed for. And we can see that this is borne out, both in protons and neutrons, approaching the scalar limit as you go to high relative momentum in very, very short distances. Now, all of these experiments are difficult to interpret because there's an unavoidable competition between other reactions with the same final state. And so we would love to be able to interpret the measurements that we make in terms of a plane wave model where we can understand this from the initial wave function of the nucleus, but this is going to unavoidably mix with amplitudes from other final state interactions and other reaction processes. Now, the guidance that we've developed for ourselves in the past over a decade of research is that you should go to anti-parallel kinematics, and this is a theory calculation comparing a full cross-section, which includes all of these additional reaction effects, to one that's plane wave. And you can see that the two converge if you go to angles in which the missing momentum is very, very anti-parallel to the momentum transfer. And that's a place where the rescattering effects and final state effects seem to be fairly minimal. And that was the guidance that informed our experiment during the 2018 Hall A tritium program. We made a measurement of the E'-P reaction. We did a coincidence measurement with both spectrometers We were one of 5 experiments in this program, and we were the ones to do a coincidence measurement on E prime P. And what we were expecting to observe is this transition into the NP dominance regime. So if you imagine counting protons in helium-3 versus tritium, which is equivalent to counting protons versus neutrons in helium-3, we were expecting to see in the low momentum range to basically expect nucleon counting. There's twice as many protons as neutrons, and we'd see a ratio of about 2. Eventually, as you transition to the short range, high momentum regime, this would give way to the NP dominance prediction about a 1-to-1 ratio. And this is what all of the theoretical models predicted for us. Instead, we saw something far more interesting. So the data actually at high momentum go above all of the theory predictions and show an unexpected rise. We didn't know how to interpret this purely from a ratio alone, and what we did instead is do the extra work to get absolute cross-sections. So this is grace of some very, very talented students and postdocs. We were able to turn this analysis around in less than 2 years after data taking. We were able to get absolute cross-sections. And what we found is that this guidance of going to anti-parallel kinematics, in which the angle between the missing momentum and the q vector is anti-parallel, or in consequence of this is that we're looking at x Burkane much, much greater than 1, is that the plane wave predictions do a much better job of matching data than previous data in XB of around 1 kinematics, which are shown in the open circles. So here's 2 different plane wave models looking at the helium-3 proton knockout cross-section, and you can see it's the PWIA models do a much better job. If we compare this to tritium, the same thing is held true. However, if we look at them together and we try to incorporate the calculations of final state effects, we see this incredible divergence where the helium-3 goes above the theoretical predictions, the tritium dips below. And we've now understood that there's one ingredient that's missing in this theoretical calculation, which is an effective single charge exchange with the residual system, which, because the residual systems are different, ends up being charge asymmetric for the 2 systems. And so what we actually can do is form the isoscalar sum and do a fantastic job of being able to reproduce theory in spite of all of these extra final state effects. This was a huge realization for us, and helped cement a number of big lessons from the Hall A measurement. One, this idea of going to anti-parallel kinematics is really, really effective at reducing final state interactions and helping us actually interpret the measurements that we're making in terms of the initial state. 2, going for absolute cross-sections is vitally important. We can't simply rely on taking cross-section ratios and expecting things to make perfect sense from the get-go. Lastly, it's really important to get helium-3 and tritium, to get both sides of the isospin mirror, and other light nuclei too can help constrain. Having both sides of this isospin system allow us to form isoscalar sums and allow us to reduce the effects of other competing reaction mechanisms in other ways. Now, we can explore the repulsive core up to high momentum. There's a whole bunch we want to do. If we can push out the missing momentum out to a GeV, we can really nail down and help explore the isospin structure of the NN interaction in extremely high clarity. We also would love to cover a broad range of kinematics where we can actually test the onset of these final state effects as we change the orientation of the different angles of momenta that we're probing. So that's the motivation. However, this is going to require putting tritium in Hall B, which, as we know, is no small effort. And I argue that we've got a safe and feasible plan, which I'd like to just sketch out for you. We have a target design for how this could go in class 12. It's produced by Dave Meekins, one of our spokespeople. Now, tritium, being a safety hazard, needs to be enclosed in a sealed cell. And so we have a sealed cell design. You can get about 1.2 kilocuries of tritium and do so in a way that fits into the class 12 bore. Now, this would be replaced by a simple refillable cell and a simple gas handling system to have gas targets for other gas targets that we'd like, hydrogen, deuterium, and helium-3, as well as empty. And we estimate about half a PAC day in order to change cells. The total target's about 25 centimeters in length. It gets full azimuthal acceptance. Acceptance at 120 degrees. And because of that azimuthal symmetry, it's actually easier to fabricate than the Hall A cell design, which had that target ladder and had to have different cooling requirements. It involves many more windows and a little bit more material than is traditional for a typical Hall B target. we've taken this into account. So here I'm showing the thicknesses and the effective luminosities of the tritium, but compared to the aluminum windows, which hold the tritium cell, the beryllium vacuum window, and you can see we've designed it so that the total luminosity on target matches sort of the limits of the class 12 running conditions. So you can see that a fraction of the luminosity is actually usable on tritium. Most of it's on the windows. That's okay. This is exactly how we ran in Hall A, and I'm showing the Hall A electron vertex spectrum. So you can see that the Hall A target was aluminum with a little tiny bit of tritium in between, and that's no problem. We can exclude that aluminum with vertexing cuts. And so what we've assumed in this proposal is a very, very safe, conservative 15 centimeters of usable target, 2 e to the 34 of usable luminosity. That's absolutely suitable for our design. Now, a tritium target system needs a multiple levels of confinement at all times. And so we've worked out a system based on the experience we've gained the Hall A target of how to make sure that that's maintained during the installation stage, the storage stage, when beam is on target. We've got safety systems in mind. All right, so let's take a look at what we can do with tritium and helium-3 in Hall B. So the big advantage of going to Hall B is that class 12 lets us vastly exceed the kinematics of what would otherwise be limited in Hall A by the narrow spectrometers. Now, tritium is a luminosity limited target. We just can't put that much beam safely on a tritium target. And so if you're limited in luminosity, it actually makes sense to try to make up for that with acceptance. And so going to a large acceptance spectrometer is a much better plan. It actually is not even a trade-off. It's a huge win, a factor of 100 additional statistics. So now we have the kinematic coverage to study Q-square dependence, X-Burkane dependence, the angles between momentum and momentum transfer dependence. We can get to higher missing momentum, wider coverage in EMIS, and we can do this all at the same time. So here I'm showing just the... Yes. Say that again?
You have 5 minutes left.
5 minutes, perfect. So here I'm showing the phase space that class 12 can cover in Q squared and X. By comparison, what we were able to cover in Hall A is a small wedge in that. Here's the angle between the missing momentum and the Q vector versus missing momentum. You can see that we have coverage all the way out to a GeV over C. Again, these are the events we had in Hall A, the little trickle, the couple hundred events that we had after physics cuts. Same thing is true with missing momentum and missing energy. Again, we push out all the way out to a GeV over C in missing momentum. And again, in Hall A, we were able to cover just a narrow sliver of that and get a couple hundred of events. So what we want to do, we want to make quasi-elastic measurements on these A = 3 nuclei. And we can do it in a few different reaction channels. By looking at E'P, we can look at few body nuclear structure. If we can also, with a large acceptance, get triple coincidence. We can look for the correlated emission of a second nucleon and look at short-range correlated pairs. And lastly, we even see that we can, with inclusive, we can look at the neutron form factor. Taking a look at these in detail, if we look at E'P, we have a great test of few body nuclear structure, and we can actually benchmark in sophisticated few body calculations with high degree. This allows us to study both the short range and an interaction. It allows us to study reaction mechanisms and final state effects. And again, even though we're reducing luminosity, we had a luminosity limited target. So with the increase in acceptance, we get a big enhancement in statistics and kinematic coverage. Again, this is what we were able to cover in Hall A, and we would be able to push out much further missing momentum. In triple coincidence, we would allow us to map out the isospin structure of short-range interaction between nucleons and the effects on short-range correlated pairs, and give us a detailed map of that. And lastly, if we look at around XB = 1 for comparing the inclusive helium-3 and tritium cross-sections, we're actually sensitive to the magnetic form factor of the neutron. And because of the coverage of class, if we reduce the beam energy for just a couple days at 2.2, we get amazing coverage at low Q squared, right where there's some exciting discrepancies between data and theory. And this technique is really nice because the systematic errors are orthogonal to those using other techniques, chiefly scattering on deuterium. Our beam time requirement breaks down as follows. It's 60 days with including time for calibrations and overhead, 53.5 days of actual total measurement. We get incredible statistics and cover a much bigger range of phase space. And quickly to summarize, I tried to argue that the A = 3 mirror system is really vital because it not only gives us really good predictions that can be tested by calculable, sophisticated machinery in the few body regime, but it also allows us to test the extremes of proton-neutron asymmetry and take a step toward neutron-star matter. It allows us to constrain reaction effects because the residual system is much simpler, and allow us to probe the short-range interaction to have very, very high momentum in short distances. And we even get an extra GMN measurement as well. The thing is, we need both helium-3 and tritium to do this. For this, we're proposing a new target system to go inside the standard configuration of class 12. And one of the reasons we're really seeking the PAC imprimatur for this experiment is because it takes a lot of work to develop this target system. So giving the motivation for this work to begin and to get all of the approvals and go through this process would be very, very helpful. I'll just conclude. There's a number of high-impact measurements that could be produced from this data, and we're really excited about it, and I hope you are too. Thank you very much.
Thank you very much indeed. So I call on the first reader of the proposal, who is again Shinya Sawada. Please, Shinya.
Yes. Could you repeat the necessity of the deuterium measurement?
Can you say that one more time, please?
Yeah. Could you repeat the necessity of the deuterium target?
The sensitivity of the deuteron target?
Necessity.
The necessity of the deuteron target.
Yeah.
Sorry, or did you want to jump in?
Go ahead.
Go ahead. So the deuteron target is valuable because, one, it gives us an additional way to do calibrations. Two, it's an additional light system for which these same predictions work, but in which the kinematics are restricted by an additional degree of freedom. It's just a powerful lever that doesn't need only needs a few extra days of running to get an additional handle. And that was shown because we included the deuteron results in the first paper from our Hall A program, and that was actually a really nice additional constraint that we were able to include in that paper. Or did you want to add anything specifically?
No, I mean, I think you said it, right? At the end of the day, these are very complex systems, and having the full range of nuclei that are fully calculatable these days, which is deuteron, helium-3, helium-4, is what is, I think, needed in order to be able to have a self-consistent understanding of all the topics that Axel discussed. The overhead for including it is quite minimal, and the physics gain, I think you get a lot of bang for buck here. So we thought that it makes sense to include that system as well.
Thank you.
It's much simpler than helium triton, right? It doesn't carry all of the physics wealth that you have in the three-body problem. But just because, for that exact reason, it's good to have that as an easy starting point before going to the complex systems.
All right, thank you.
Do you have any other question, Shinya?
No.
Then I'd like to hand the word to Charlotte Elster, who's the second reader. Please go ahead, Charlotte.
Yeah, I would like to get a sense, or can you give the PAC a sense what would suffer if, for example, you don't get the 54 days and stuff? I mean, you had a list of things you want to do, and your proposal doesn't really flesh out. Supposedly, you get cut by some days. What actually suffers most in your analysis and what you want to do? And I think it will be very helpful if you give the PAC that kind of idea. What do you give up if you don't get, for example, 20 days, but only a little bit less?
So you give up a lot. The big thing you give up is the ability to reach to high relative momentum. So this cross section is falling quite steeply, and the length of time that we're requesting is really necessary to push out to the extremes of relative momentum, so we can actually see the onset and the signatures of the repulsive core of the anode interaction. So we lose that.
Yeah, you had a list before on one of the slides. I didn't count and didn't remember. I didn't remember the slides where you said, I mean, you're doing absolute cross sections on all that kind of thing. So Yeah. So do you remember which slide I'm referring to? And there, I mean, and can you point on that slide what you really give up if you don't get the amount of days? I mean, I kind of hear when you say that you said you're measuring absolute cross sections, and are you giving up then the very high momentum part of that absolute cross section or what?
Yes. Yes. So, I mean, maybe you can see it illustrated here is that if we want to push out to the highest missing momentum, then, I mean, the rate is low. And this is what I'm showing here, basically summarizes that if we want to be able to make any statement about between 0.8 and 1, we would lose that. Let me see if I have. The other thing is that what I'm trying to show here is that we're trying to make measurement that's differential in a number of dimensions. And we'd love to study dependencies in multiple dimensions. And again, with anything with the cursive dimensionality, this is a compounding problem if you lose statistics, right? Your ability to make multidimensional inferences just gets completely diminished.
Okay, so to reiterate, I mean, for us later in the discussion, that you need the amount of days to actually get the statistic in the high momentum transfer.
Yes, so we are systematically limited at low momentum, not momentum transfer, say, but missing momentum. So the proxy for the momentum of the nucleon in the nucleus prior to the collision. We want to go to very.
I would say both. I just want to say it's both. If you cut the beam time, you lose the high missing momentum, and even for the lower missing momentum, you lose the ability to study the Q-score dependence. When we are talking about studies of reaction mechanisms, trying to understand the phase space well enough with comparisons to iconal and all the theoretical involvement that we have here, having the leverage of a wide Q-square dependent studies that we know from all the previous studies that were done so far is a huge handle, and we're just going to lose that one. So for the reaction effects to interpret all the data, it's the Q-score dependence. For the physics reach and the impact of the measurement, it is the high PMIS, high EMIS, which also relates, if you'd like, to questions, for example, of free body forces, etc., in the tails of short distance free body forces, in the tails of the nuclear wave function. Right? There's a quite famous paper by Gandolfi and Reddy about equation of states, etc., where they talk exactly about how the short distance free body forces are what's really sensitive to that, and the place that those appear to a certain extent, it's very hard to nail them down, but definitely if we can say something about them, it will be at the very high PMIS. This is a huge installation, not huge, but this is a major installation. It's not a small project. So we think that, we can cut 10, 20 days here or there and save the beam time, but this is something for you guys to discuss, but in light of the installation and bringing the tritium target and how much it costs, etc., I think it makes sense to get as much out as we can from this target if we're putting it in such a remarkable detector like class 12.
Okay, no, thank you. That was very helpful for our discussion, which was not as much worked out in the written text. Thanks a lot.
Thank you very much. Is there any other question from another member of the committee? Perhaps I can ask a question. Can you go one slide back? No, I think it was 39 when you had the data and theory curves for the magnetic form factor. Yes, you pointed to an apparent discrepancy in theory predictions. I wouldn't really call it that, because certainly the green curve, which I was one of the people who produced it, that was a fit to data that were available in 2004. It essentially fitted the data points that lie on top of it. And when we redid that kind of exercise a few years ago, we actually excluded that data because it is so much in contradiction with anything else that's been measured since. So this is really not a theory prediction. It was a fit to old data. And I suspect that a similar statement is true for the curve by Michel Vidal and colleagues. So I think one has to be a little bit careful here. What is a theory prediction and what was a fit to data at that point in time?
What I can say from the experimental side is that we can cover this range with basically a high density of measurements with extremely small errors and really nail this down. And so that there won't be any ambiguity between deuteron measurements and helium-3 measurements. You can judge the size of the error bars of the data available. There's quite a bit of room for variation.
And exactly because theory is so complex and a lot of what we know is data-driven, it's fixed. That's why we need those red points, right? Those will help guide exactly how the magnetic form factor behaves at low Q-square. The same concept that Marathon used for F2N over F2P, only here we're going out on the neutron form factor. I think this will have a big impact.
I think I agree. Thank you very much. If there's no other urgent question, I would close this session. Thank the speakers again, or the participants. The open session of the PAC will resume at 11, and the PIC now reconvenes in closed session. Thank you very much.
Bye.